Okay, we are live. Welcome, everybody. Professor Trevino. This is week number 2 of the business math class. And earlier in the week, we talked about exponents, radicals, and logarithms. But later in the class, or later this week, right now, we'll talk about the time value of money problems. Starting this week, we have simple interest problems. And next week, in the next couple of weeks, we'll have several different growth methods that we'll use. They all fall under the TVM framework, the time value of money framework. And so I'll be using words like present value and future value for all of them. But if you searched online for present value and future value, you probably get a very specific formula for a very specific kind of growth. And while that's not wrong, right, it's probably not what you were looking for to answer the questions that were on your homework. So let's see if we can clear up some of that confusion with a little bit more details. And so the time value of money framework basically is a way to understand how money isn't the same over time. Right? Most of us kind of get an inherent understanding of this. Right? $1 today is not the same as $1 in 1980. I mean, $1 today is not the same as $1 in 1930. Right? So the value of the money itself has changed over time. Right? In economics, we would talk about inflation and the difference between the real value of money and the nominal value of money. But here in business math, we're more concerned with as the money grows over time, right, with interest rates and bank accounts, how can we measure that? Right? So we're going to focus on sort of the bank accounting sort of time value of money. Um, the first time value of money, let's do the definitions first, right? When we talk about time value of money, we're always concerned not just with the value, but exactly when that value applies. So I can start, if I start at any point in time, and I'll start with the present value. That's usually what we're talking about, right? The starting day is today. The present value of any bank account, any amount of money, stocks, CDs, right? That's the present value. And as that grows over time, it will eventually grow into the future value, right? The PV and the FV, present value, future value, or the ending value. And the way that it grows between kind of depends on what kind of investment, what kind of bank account it is. Like I said, if you searched the internet for present value, you would find information about one specific kind of growth, but the time value of money framework applies to all kinds of growth. The most simple time value of money problem I like to call, scenario 0, it's the money under the mattress. Yeah, it's not exactly changing, but I can talk about the present value and the future value of money that I put underneath the mattress. Say I put $300 underneath my mattress to save for a rainy day, right? And I did that today. I would call that the present value. And what if I came back to it at Christmas time, which is maybe 4 months from now? Well, unsurprisingly, there would still be $300 under the mattress. It hasn't gone anywhere. Hopefully, I don't have any bugs that try to eat away at it. But it hasn't grown any either, right? The present value and the future value are exactly the same. So there is no growth in between, not for the under the mattress case. So it's kind of weird that in this very simple case, the present value is equal to the future value all the time. And there is no growth happening here. Sorry, I wrote that 300 on the wrong line. There is no growth happening. But that's not the interesting case, right? There's no homework questions about the under the mattress case because it's not interesting, right? Nobody cares about the money that we put under the mattress, right? We want to talk about money that's growing in a bank account or something like a bank account. And so we want to talk about other growth methods. Right? And the first growth method that we're really interested in is the simple interest method. You don't see simple interest that often, except we have one very specific case where we do see it very often, right, with the bonds. But as far as putting your money in a bank, you don't see simple interest that often. And the reason for that is because simple interest is a step for step. That is, I'm going to put it in the bank and it's going to draw interest, but that amount of interest is the same every time. And I know what you're thinking. Well, don't all bank accounts work that way? Because I put my money in the bank and I get a 0.5% on my savings account, and every year I get 0.5% and 0.5%. But it's not the same, because if you think about it, that 0.5% from one year to the next is not the exact same money. In the simple interest case, the amount that I'm talking about adding is exactly the same dollar amount from period to period. So let's take that same $300 present value, and I want to deposit this into a bank that pays me 10% simple interest per year. And that's a lot. Right? But the simple interest part of it tells me how it grows over time. And so I could look at this and say, after 1 year, right, the future value is equal to the present value plus 10% of that present value. The way you can think about that is that at the end of the year, I have the money that I started with, that's the present value, plus an additional 10% of what I started with. This is the interest amount. Sometimes the formulas will use a big I to put on this, right? A big I and big P and big A, right? All of those letters represent dollar amounts, right? Little letters like little I or little r usually represent percentages or rates. I mean, they'll usually use a lowercase r, for example, to represent the interest rate. That's not a hard and fast rule, but it is a good framework for remembering how to read these formulas. And if I wanted to calculate the future value after 1 year, I could plug in the present value, which I know. I'm going to change that 10% into a decimal, 0.10 times the present value, $300. Go to my calculator really quickly. It tells me $330. And so this would be the future value after 1 year. I could repeat that process for after 2 years. And in the simple interest case, the amount of interest that I earn, that big I, is going to be exactly double, because in the second year, I'm still earning 10%, not 10% of what's in the middle, right? You might be more familiar with that if you have a bank account. That's compound interest. We'll talk about that more specifically next week. In compound interest, you get 10% or whatever your interest rate is of whatever your balance is at the end of the month, right? Most people are familiar with that, like credit cards, right? My credit card interest rate is 15%. And so the interest that I pay is depending on what my balance is at the end of the month. It's not this sort of, it seems like this is almost like a prearranged amount of interest. You don't see it that often with banks. So, future value. Future value after 2 years would be the present value plus 2 times, because it's gone for 2 years, 10% times the present value. And we'll make this into a more generic formula, which you can box in and write down on your note card. So when you take your exams, you can have a better formula. This is just helping me understand where I get these numbers from in the first place. Right? It looks almost exactly the same as the 1-year case, only I multiplied the interest part times 2. 300 plus 2 times the decimal times the present value, 300. Go to my calculator really quick, type that in, and I get $360. So that's not too bad. If I were to keep track, if I were to keep a table of all of this and keep this going 3 years, 4 years, 5 years, okay, I would see that the amount of interest, the amount of interest that I earned in that first year, starting at $300 and ending at $330, the amount of interest that I earned was $30 interest in the first year. And for the second year, between year 1 and year 2, it would also be $30. If I calculated it beginning at all the way to the beginning to the end of year 2, I would say my I would be $60, right? 2 times the $30. But if I'm only doing it between the end of year 1 and the end of year 2, I would say, well, that I is $30 extra. And together they would be 60 for both years combined. You see, the interest amount, actually didn't change between the first year and the second year. That's how I knew this was simple interest, right? Or more likely, I would be told it was simple interest, and so I would expect that that would not change. We don't do a lot of graphing in this class, but if we did, our graph would look something like this, right? On the x-axis, I would put my time, and on the y-axis, I would put the future value. And it would begin at some point, right? The y-intercept there would be the present value. That's how much I have now, today, and t would be equal to 0. And it would be a perfectly straight line over time. And that's because I get the same amount of interest every single year I leave this in the bank. So simple interest, the formula that we're about to write, it will look exactly like the formula for a straight line, if you're familiar with it from a previous algebra class. Simple interest is a straight line growth. Not super realistic. Like I said, your credit cards don't work this way. Most of your bank accounts don't work this way. Bonds do work this way, and in a kind of weird backwards way. We'll see bonds a little bit later. But simple interest is a straight line growth. And so let's write the actual formula for growth with simple interest. And it keeps popping up because I've got a second program to throw the video from my tablet to my big computer. And so it doesn't work with a touch screen quite so well. The future value in simple interest is going to be the present value plus the rate, the interest rate, and that would be the 10%, times the present value times however long I've actually invested this money times t. Now, those variables probably are all goofed around from the formulas you're used to for simple interest. If you'll give me one moment, we'll try to make that into something you've seen before. What I'm going to do is I will sort of factor out that PV, present value. When I factor it out, it has to leave behind a 1 plus R times T. And if you want to double check that I've done that factoring correctly, you can distribute, right? PV times 1 is PV. That takes care of this one. And PV times R times T gets me PV times R times T, the second part. So I've done my factoring correctly, but I bet you've seen this formula in the second form a lot more than you would have ever seen it in the first form. Matter of fact, if you looked up this formula on the internet already this week, you probably have seen something just like this, only they didn't use the letters FV and PV to deal with this. They would have put it like this: A equals P, parentheses, 1 plus RT, like so. And you're going to see that quite often, right? So in financial formulas, P stands for principal, PAL, not PLE. And that's how much money you started with. When it comes to the time value of money framework, that will always be PV. So anytime I write PV in a formula, you can switch that out for P. It means the same thing, how much money that I started with. A, right? I'm not exactly sure what A stands for. I usually call it sort of the accumulated amount or the final amount. But it is the future value. Right? So anytime I use the future value in a simple interest case, that is what A is. Right? So this is probably the version of the formula you find in your textbook and online. A equals P times 1 plus RT. But we still have to be careful, even with this nice, convenient formula, right? Because in this case, the A is going to be measured in dollars, usually. The P is going to be measured in dollars. So if A is measured in dollars and P is measured in dollars, that must mean whatever's inside the parentheses there doesn't have any more units, right? Because if the parentheses in there were, other units, that'd be like dollar months or dollar meters or something weird like that. Let's see, R is going to be measured as a percent, but a percent is not a unit, right? A percent is just a decimal, right? And usually a percent per some time unit, percent per year, percent per month, percent per quarter, right? Some kind of percent per something. And then the T is measured in that same exact time unit. And so those time units cancel each other out. That's why the final answer did not have a time unit on it. That brings up a really good thing to remember, is that R and T have to be measured in the same time units. So if my interest rate is percent per year and my time is measured in months, I can't plug that straight into the formula. I would have to convert the number of months to a number of years and plug that in instead. I believe there's one just like that on your homework, where it asks you to calculate the future value for 10 months or so into the future. Well, if you have that percentage per year, you might have to multiply that times 10 out of 12 months. And 10 out of 12 months would have to be a fraction at that point, 10 over 12. You would have to plug that into your calculator either as a fraction or work with it correctly as a decimal. And unless otherwise specified, Your R is going to be a yearly percentage. You've probably already seen homework problems that give you a rate. They say, oh, well, it's 6% interest. Well, 6% per what? I have to have a time unit there. And so if there's not one given, you can assume that it's a per year time unit. Right? That would be the annual rate, the APR. You might have seen this on another textbook page or a notes page. Annual percentage rate. I bet you've seen this if you have a credit card or something, you've probably seen a rate expressed as an APR on those documents. You hear it on the commercials all the time, right? Well-qualified buyers, right? 1% APR for 60 months. The APR is the yearly percentage rate. And when we talk about simple interest, that is the amount that you'll get back. Right? That is, if I look at the beginning amount and the ending amount, it is exactly that number of percent bigger. Right? We won't make the difference today because there's not a difference. But when we talk about compound interest, we will make a difference between the APR and if we left the money in the bank and came back a year later, would I actually have 10% more, or would it be a little bit more than that? It will be, right? We'll introduce a different concept then, talk about the actual yearly growth. It'll be a different rate. But for simple interest, it is a straight, this is the APR. Let me grab a problem from our homework. I'm going to do it on the keyboard, which is going to be a little weird looking because I didn't set up my pen correctly. You know what? Let me just fold it out. I usually set up my pen to grab a screenshot whenever I click the button on the top, but I just remembered that I got a new pen and it's not set up the same way. There we go. Let me grab this question. I don't care about the answer box. There we go. Hey, look at that. It's almost like technology works sometimes. Of course, I've cursed myself by saying that. So this problem, suppose you have $1,700 in your savings account at the end of a certain period of time. Okay, I highlight the word end because that tells me that this thing, the 1,700 number, is the future value or the A number in my simple interest formulas. You invested $1,300 at 6.61% simple annual interest rate. Okay, so that tells me I started with $1,300. That's the present value, the P for my simple interest formula. And it told me what the interest rate was. Simple annual interest rate. Annual means per year. Simple means simple interest. Right? Anytime you're dealing with simple interest, it will always have to say simple interest. Because if you weren't dealing with simple interest, right, I would say something different. Right? As a matter of fact, if I don't say anything at all, I'm talking about compound interest. I have to specify simple interest. Simple annual interest rate. How long in years was your money invested? But that's the T number, and I don't know how long that was. I'm looking for it. Move this down because we were told the R, 6.61% is R, and I don't know what the T value is. right? I'm going to make it a really good habit of mine to always give my R values as decimals, not percentages. 0.0661, right? You always move the decimal place twice. And percentages less than 100% should be less than 1. Right? That always helps me remember, which way do I go again? If I move the decimal place 2 in the wrong direction, it would be 661. It's like, wait a minute, that's not right. I expect this percentage to be somewhere between 0 and 1. Right? And if I move it to the right, it's the wrong way. I don't end up with a number between 0 and 1. I move it this way once, and then I have to add a 0 to move it the second time. 0.0661. That's the decimal I'll use in my formulas. Let me set it up. I will use the A equals P version of the formula. 1 plus RT. Like I said, that's the one you're most likely to see. So let me plug in some numbers. 1700, 1300, 1 plus decimal times T. I don't know what T is. So here I've set up a equation. To solve for T in this case would be to solve for the amount of time. Well, we've been looking at equations and other algebra in our review assignments for weeks 1 and weeks 2. So let's see, I see some multiplications, I see some additions here. I could distribute this 1300 like this, but I'm not really sure I would want to do that just because I'm lazy. What I see when I look at this and I say, well, what if I divide both sides by 1300 right away? Dividing by 1300, it lets me cancel out that 1300. And I don't ever have to worry about multiplying 1300 times that decimal. Right? Whenever you're working with decimals, do your very best to not work on them unless you absolutely have to. Because every time you round your answer, right, it's going to be a little bit more wrong every time you round it. And yeah, in this class, the numbers aren't generally big enough that that little bit of wrongness will add up to the wrong answer in the end, but it quite possibly could, right? Certainly for banks it does. They're dealing with trillions of dollars. But you don't have to get that big to start noticing an error, right? If you did this with a bank account larger than $100,000, you would start noticing the errors. They'd be small at first, but they would start to add up quickly. So I'm not going to simplify my fraction just yet. I will simplify it in the next step. And once I cancel out the 1300, all I'm left with is 0.661 times t. You notice I've written this without the explicit multiplication in between the decimal and t. All right, I feel like I'm on my way now. Right? Now the nice part about this is because this is a business math class, we don't have to actually figure out what 1300 divided by 1700 is. I know it's some kind of decimal, right? But let the calculator deal with that when it's time, right? If you really want to start simplifying this, right, I would tell you to knock the 1300 and the 1700 down to 13 over 17. That would essentially be dividing both the numerator, the top part, and the denominator, the bottom part, by 100. Right? So canceling out a common factor of 100. But even then, you don't have to do that. Right? You can let your calculator handle that at the end. As long as you type it into the calculator correctly, it will deal with it. I can minus 1 from both sides. It's going to look a little silly. 1300 divided by 1700 minus 1, like that. Don't try to put that minus 1 inside the fraction. So it looks a little silly, but I can deal with that. 0.661t. And now all that's left for me to do is divide again. And this is why some students prefer to simplify or work with decimals as often as they can, because they say, Professor, you've just got this weird big fraction inside of this other big fraction, and I don't like you anymore. I don't like that you have done this to me. I promise that to type this into your calculator is not as bad as it seems. If I were to type this into a calculator, I would type 1300 divided by 1700. If you wanted to, you could put parentheses around that, but it wouldn't be required. Minus 1. This set of parentheses is required. And I know a lot of students don't care to memorize which ones are and which ones are not, so they want to put them all in there. More power to you. Put them all in there if you're afraid that you won't get it right. Divided by 0.661. Basically, I'm following the order of operations. Right? The order of operations says go inside the fraction. In the top part, I see a division first, then a subtraction. Right? So that's what I've written down, 1300 divided by 1700, parentheses, minus 1. That's division first, then subtraction. And then outside that, do the big fraction, all divided by 0.661. Well, let me see. Oh, I haven't installed. Sorry, this is a new computer for me, so I did not install my calculator application. I will do it on my big computer. On the ones before, when I said I'll bring out my calculator, I cheated. I did it in my head. This one I'm going to have to do manually. Minus 1 divided by 0.661. And you could do that with 2 steps in your calculator. Some people will do this in individual steps in their calculator. They'll say, well, I'm going to type this part in first, press enter, and then do minus 1, and do this part second, press enter again, and then divide by 0.61 to do it in 3 steps in their calculator. And that's fine, right? But that requires you to know what the correct order of operations is. And if you know what it is, more power to you. I will never stop you. Right? I was just listing it all out as one big calculator entry just because I wanted to give the option there for students who wanted to see their calculator do all of that, and so they didn't have to worry about it. Uh-oh. Did I do this incorrectly? Let me retype it. I got a negative number in my calculator. Oh, it's because I typed it into the calculator wrong. Put the 1300 on the top of the fraction instead of the 1700. Right? So this is a good point to say, right? I got a negative number in my calculator, which would be a negative amount of time. That's probably not right, right? And I started panicking right away. I was like, oh my God, not only did I mess up, I messed up while I was recording, right? For everyone to see that I messed up, right? And that's okay, right? We don't have to get all this right the first time, but we need to practice it so we don't make a lot of those mistakes. So let's see what it says. This would be my t value. T would be equal to, now it gives me a decimal number here, 0.465465. It keeps going. It's a big long decimal. Let's see. The computer asked us to round this number to the nearest hundredth of a year. And so this is measured in years. The nearest hundredth of a year, let's see. That's we have to take that decimal word and change it into a number of decimal places. The easiest way that I can remember to tell you to do it is think about the number. The number 100 has 2 zeros. So if you round to the nearest hundredth, that's 2 decimal places. So I want 2, and I would round using the third one. So that is approximately, or rounded, 0.47. The 5 makes it round up to 0.47 years. And that works for any decimal word, right? If I ask you to round to the nearest thousandth, If you wrote out the word 1,000, that has 3 zeros. And so that means 3 decimal places to round to. It's probably one of those things you might be doing. Why has no one ever told me that, Professor? Right? I've always hated word place values and decimal word place values even more so. Right? But knowing that, I could ask you to the round to the nearest 100,000th, and you would say, oh, well, maybe that's not so bad. If I wrote out 100,000, that would take 1, 2, 3, 4, 5 zeros. Right? So that's 5 decimal places. The answer is really as difficult as it feels like it should be. But anytime you have questions like that in this class, that was like a question like buried way deep in here. Feel free to ask in the boards, ask me in the email. I'm full of all kinds of little tips like that. You don't have to struggle on your own. If you could learn all this stuff on your own, well, and it wouldn't be a hard thing to do, you probably would have already done it by now, right? Everyone's going to struggle a little bit, right? Let me help you make it not quite so bad. Our answer is 0.47 years. I'm going to go beyond the text of this question and ask you how many months that is. Right? Let me take this and round it to some whole number of months. So I'm going to go back to the full decimal, not the rounded decimal. Anytime I do rounding over rounding, it'll be back to the full decimal. Well, I've got some decimal number of years. Right? So how many months is that? And again, people freak out. If you're in a science class, we would do this whole thing with conversion factors. But let's think about it for a minute. If I told you this was exactly 1 year, how many months is that? 12. So if this was exactly 1 year, that would be 12 months. This is about half a year. So this is about 6 months. And if I wanted to be super exact about it, I would multiply times 12, right? 1 year is the same as 12 months. That's times 12. So let me take the big long decimal and multiply it times 12. I'm going to go back to my calculator, which I haven't cleared. So I'm just going to do times 12, the answer times 12 in the calculator. 5.5859, and it keeps going, months. So if I rounded that to a whole number of months, that would be 6 months. But you probably weren't surprised about that, right? Because you saw that the original decimal was really close to 0.5, and 0.5 is about 1/2. So maybe this doesn't surprise you that it ended up being about 6 months. If I asked you to round it to the 10th of a month, it'd be kind of weird, right? 10 has 1 0, so 1 decimal place for 10th. That'd be 5.6 months. But we rarely round to a lot of decimal places when it comes to time. Right? 2 decimal places is about as far as we would ever go for years. 1 decimal place is even kind of absurd for the some number of months. And I definitely ask for any decimal places if I had a time value smaller than months, like weeks or days. And I don't want to know like 2.6 days. That's not useful. We'll try to stick to rounding to values which are actually useful in this class. Hey, so that was some neat points about rounding, right? And a good question from our homework, right? To bring it back together. So that's simple interest time value of money. Right? Before I let you go, right? I want to talk about bonds a little bit, just because we started talking about them in the My Open Math. There's a page about it in the My Open Math. If you go out, and I believe one of the questions is a bond question, or did I take that one off? Oh, there it is. Question number 11. Ooh, yeah. So this one's a big one, right? There's even a table there, right? You can tell whoever coded this question, it was me. Whoever coded this question is a very mean person. You probably shouldn't hang out with him. I mean, this is about bonds. I mean, it's all about bonds. And if you notice, it talks all about bonds much the same way that it talks about bank accounts, right? I purchased a bond for some amount and it gives percentages like it might for a bank account. Right? But it's talking about selling of the bond. So let's do a brief overview of what bonds are and how we can understand them in the same breath as we understand the time value of money problem. Right? So you can think of a bond as an old school sort of clip out, right? It's like the precursor to stocks. Right? A bond is basically just a big piece of paper that says I owe you. Right? It's a big IOU. Right? And what would happen is that companies or governments would sell you a bond, right, in order to borrow money. Right? So the government would print this bond, and on this bond it says I owe you $1,000, but I'm not going to pay you now. I'm going to pay you on a future date. That date would be on the bond. Let's just say 2021 because that's about, next year sometime in the future. And you would hold on to that bond, right? And if you walked up to the government on that day, you could cash in that bond for the amount of money that's on that bond, cash for $1,000. Simple enough, right? If I bought this bond and I paid $1,000 for this bond, then you might think I'm a sucker, right? Because I'm just lending the government $1,000 and I'm going to get $1,000 back. I'm not going to earn anything on that, right? Out of the goodness of my heart, I have let the government borrow this money and I'll get it back from them at a later date. But that's not usually how bonds work, right? Usually, right, when I buy a bond, right, the purchase price doesn't always match this price that's on the front of it. Okay? That's called the face value of the bond. And the maturity value, right, is equal to that much money. Right? This is called the maturity date, by the way. If you get to the maturity date, you can cash in for that much money. And so in many ways, right, we've got present value here and future value here, just like we did for simple interest. Right? This is a very simple bond, which doesn't have any payments in between. Right? We'll talk about some bonds in a minute, which do. But this is a bond where everything about it is measured in dollars. Right? Notice how there's no percentages listed anywhere on this bond. This bond doesn't say, I'll pay you 2% interest. This bond says, hey, look, I'm going to pay you $1,000 at some point in the future, and I'll let you decide how much interest that is based on how much you're willing to pay for this bond today. And so let's say that I buy the bond, and I'll make it exactly 1 year to make the numbers nice and round. I'm going to buy this bond on January 1st, 2020, and I buy this bond for $900. Okay? Again, whoever buys the bond, right, and whoever sells the bond determines the purchase price, right? It says $1,000 on the bond, but that doesn't mean I'm going to pay $1,000 for the bond, right? If that's not what it is, it's like going to the shoe store, right? And it says $20 on the box, but no one ever pays $20. They always wait until it's like 60% off. Right? You always get a discount on that price. Same thing with bonds. So if I buy it for $900, that's going to be my present value or my purchase price. I'm talking about bonds. I wouldn't call it the purchase price, but that is the present value if I'm using the same time value of money terminology. And then I wait until the maturity date, 1/1/2021, and I can cash in this bond for $1,000. That's the future value, or what I would call the maturity value if I were talking specifically about bonds. So let's analyze this bond the same way that I would analyze a simple interest bank account, just like the homework problems we did a minute ago. I'm going to pull out my future value equals present value times 1 plus RT formula. I'm using the future value, present value version because this is not a bank account. I don't have an A and a P. Well, I know the future value, and I know the present value, and I know how much time it was in between, the T. That must mean I can solve for the R. So let me do that. Let me solve for R by plugging in these numbers. Exactly 1 year. That makes it a little bit easier. Okay. Again, I could distribute that 900, but I am lazy. And I would rather divide everything by 900 first to get rid of it. And it looks like I can divide both sides of that fraction by 100, just like the last problem. You could do that or you could not. Your calculator will handle that. Just to make the fraction easier on my mind to keep writing, I'll go ahead and reduce that fraction. But you do not have to reduce that fraction. Right? Your calculator will handle all of the hard work and calculations for you. 1 plus R times 1 is just R. Yeah. So let me minus 1, just like I did before, minus 1. R equals 10 over 9 minus 1. Okay. I don't even have to do that weird fraction over fraction nonsense that I had before. Again, I apologize that that keeps happening. It's like I'm using, it's like TeamViewer or something, that I'm going back and forth between the two computers. And the big computer doesn't have a touch screen, so it's really confused because the tablet's like, wait, I thought this was a touch screen. Nope. 10 over 9 minus 1. Now that gives me a decimal, 0.11111 repeating. When it comes to percentages, right, we know to change that back into a percentage, I take this decimal place and I move the decimal place twice. Which direction? Well, let's see. If I moved it this way, that would be 0.0011. That doesn't sound right. If I moved it this way, that would be 11.11111%. That sounds about right. I feel better about that. And if I wanted to round that, usually I'll either ask you to round it to the nearest whole percent, or I might ask you to round it to the nearest tenth of a percent. Right? Got to be careful about that. I'm going to write it down. Got to be careful because if I'm looking for the nearest tenth of a percent, that tells me round it to the tenths place, but don't do that until you make it a percent first. So I've already made it a percent, 11.1111 repeating. Now I'll round it to 11.1, 1 decimal place, percent. 11.1% would be the equivalent interest rate for this bond, 11% per year, 11.1% per year. And I have to say equivalent because a bond isn't actually a bank account. it doesn't actually have an interest rate on it. This is the equivalent APR, but that was wholly dependent on how much money that I paid for it. If I paid more than 900, then the interest would actually be less because I would be getting less. Right? That is, the interest amount would be less, right? If I paid 950, then my interest is only $50 for the whole year, and so the rate would be lower. If I paid a lower price, like say if I paid 500 for this bond, then I'd be getting an equivalently higher rate because my interest is much higher over the same amount of time. And so I go into this in the page on my Open Math. But when you're talking about bonds, the purchase price and the equivalent interest, they go in opposite directions, right? A higher price means a lower rate, and a lower price means a higher rate. And we'll talk more about that next week. But it's all about making it an equivalent. You see what I did? This whole problem was me taking the bond and shoving it into the simple interest formula where it didn't really belong, but I kind of made it work that way. You have to do this for all kinds of bonds. Like there are different kinds of bonds which have not only a face value on them. I buy this bond. I'll move this down a little bit so people that are coming back to watch this won't get confused as to why I drew them right next to each other. $1,000, 2025. But not only will it have this $1,000 IOU, it'll actually have little coupons on the bottom. They used to be actual coupons. They're not actually coupons anymore, but they're called coupons still because you rip them off and trade them in. You could trade in this coupon for, say, $200 at the beginning of every year. They would have dates printed on them as well. And I say, well, okay, what if I buy this bond today? Or let's let today be the beginning of the year. And I have to wait till 2025. But notice how if I wait until 2025, not only am I going to cash back in that $1,000, that's the face value of the bond, the maturity value of the bond, but all of these coupons, see, 200, 200, 200, 200, there's $800 worth of coupons there. And if I buy this bond, I'll be able to collect all of those coupons. I won't be able to do it right away because each one of them will have a date printed on it. But if I cash in all the coupons and I wait until the end, this bond will be worth $1,800 on January 1st, 2025. Well, let's see, how much am I going to pay for this bond today? When bonds have coupons, you do often buy them for exactly the face value, right? Because the coupons would represent the interest. Right? And so if I buy it for 1,000 and I get back 1,000, people say, well, that's just a wash. I'm going to treat the coupons like interest payments, right? And I can calculate the rate from there. But not always, right? Maybe you'll buy it for less than that. And they call that a discount. Or maybe you'll buy it for more than that. It's called a premium. It all depends on the financial market situation. Let's say that I've bought this bond at a discount. Right? I buy it today for $800. Right? That's a $200 discount from the face value. I bought this bond today for a $200 discount. But I'm going to hold on to it until January 25. And I'm going to cash in all of the coupons. And so on that day, my future value will be $1,800. What is the equivalent simple interest rate? I mean, the annual simple interest rate. All right, well, let me break out my formula again. Future value equals present value, 1 plus RT. I'll plug in my values. Plus R times, now how many years is this? So it's all of 2020 to 2021, 2022, 2023, 2024, 5 years, I think. So my T is 5 years. R times 5. Just like before, I'll divide by 800 because I'm lazy. Although in this case, because I don't know my R, I don't have like a big decimal there for R, I wouldn't blame you if you distributed that 800. You might think, you know what, Professor, I would rather distribute that 800 and deal with 800 times 5, a bigger number, rather than do this whole fraction over fraction nonsense. Hey, and more power to you. That would work just the same. I'm not going to bother reducing this fraction. I'm going to let my computer, my calculator, do that for me. I'm going to write R times 5 as 5R. We're used to seeing numbers written before letters, so I feel better when I write it that way. Minus 1. $1,800 over 800 minus 1 equals 5R. And I'll divide everything by 5. Right? Again, we've already seen one of these in our calculators, but you can imagine the top of a fraction and the bottom of a fraction are in parentheses. This is every fraction you look at, by the way. Every fraction will look that way. So let me type this into my calculator. I'm going to do parentheses 1,800 divided by 800 minus 1. I'm going to let my calculator handle the order of operations there, divided by 5. And my calculator tells me, oops, still writing in gray. My calculator tells me R equals 0.25. So we'll make that into a percent. Which way? To the right. So that is 25%. Here's the tricky part, though. That's over 5 years. So if I were looking at just what's the total amount of growth over 5 years, the answer would be 25%, because it is. I ended up with 25% more than I started. Oh, wait, no. I already did the divide by 5. I was about to tell you to divide by 5. I'm going to point at it because I was about to make a mistake. Look here. I already divided by 5. That 5 represents spreading it out over 5 years. So that is 25% per year. For 5 years. And I know what you're thinking, that's a lot, Professor, because if that's for 5 years, isn't that, what is 25 times 5? 25 times 5 is 125% total. Does that make sense to you? Take a half second and look at this. Does 125 cents, 125%, does that make sense looking at how much you had in the beginning and how much you had at the end? I think it actually does. Look, if this was exactly 100%, let me just round this off. If I started with 800 and I had a 100% growth over 5 years, that would mean I ended with exactly double that, 1600. Well, I didn't end up with that. I ended up with more than that. I ended up with 1800 at the end. So the total growth rate should be more than 100%. That shouldn't surprise me that I ended up with 125% total over 5 years, which when I divided by 5 broke down to 25% per year. Okay. This number turned out to be bigger than what you might be used to in your homework problems just because I made them up. And, the numbers were pretty small. Right? When you're talking in percentage terms of a small number, right, it's still a small number. But trust your gut on this one. Go back and look at it. When you get a number like a 200%, you might look at that and say, whoa, 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 whoa. That seems like a lot. Right? But go back and make sure that's really what you mean. And it looks right here. I know that it seems a little silly, like I said, to talk about this bond, which is a not super complicated, but not a straightforward money in, money out situation with all the coupons, right? Trying to force that into a simple interest situation, but it actually does, right? The fact that the coupons are always the same dollar amount and the coupons coming at regular intervals, they usually do, that is a simple interest thing. The same dollar amount at regular intervals is simple interest. And so it's actually not that crazy to stuff bonds into this box called simple interest. It'll be weirder to stuff them into the compound interest box next week. We will do that. It'll just be weirder to do that because it wasn't feel right because bonds don't work that way. And if anything, they work more like simple interest than they do compound interest. At the end of the day, all of these problems are always going to be about what's the future value, what's the present value, and how much time has passed in between. All of them are going to work that way. And so whenever we talk about compound interest next week and annuities the week after that, and it's always going to be about how much time has passed and the present value and the future value. Right? Yes, the formulas will look a little bit different depending on exactly what kind of interest happens in between. Right? But this formula, and I'll scroll back up to it, and I'll scroll down to it. I had it down here. This one here. This simple interest formula. That's pretty much all you need to know for the simple interest case. Yeah, there were some notes up above about the R needing to be a decimal and the T sometimes ends up being a fraction, right? But really, that one formula takes care of simple interest, right? Once you practice it, and that goes on my note card as one formula. And if I need to solve for PV, then I will. I'll solve for PV. A little bit of algebra. It might change how I divide or how I multiply and in which order, right? But it's all algebra, which is something we practiced during week 1. All of that, right? All 1, 2, 3, 4 variables in this equation, PV, FV, R, and T, you solve for all 4 of those variables exactly the same way, which is really nice. They're all linear equations is what I would call them as a mathematician, right? Multiply, divide, add, subtract. They're all linear. Next week in compound interest, there'll be exponents involved. And so depending on where the variable you're solving for is, we'll solve for them different ways. And if that feels like something that we talked about on Monday with the exponent form and the logarithm form, because it is. That's coming, right? Don't panic about it right now. We've got plenty of time to worry about that later. But I'm going to stop here. I don't want to go too long. Send me your questions, post your questions, right? And I will see you guys next Monday. Try to fix this keyboard thing too. Goodness.